Thank you for coming to my session. My name is Olena. I actually come here from Berlin. I really like Copenhagen, such a nice city, especially in this weather. I'm originally Ukrainian, and I actually work at Confluent, and we are a data streaming platform. So we deal a lot with use cases which involve a lot of data, and also involve some detection of frauds and detection of other problems with the data which is going in real time. And today I wanted to take some of that knowledge as well as the knowledge which I got during the researching the latest papers on the topic, where we are in the fraud detection or like in anomaly detection generally, and what challenges we have and more or less what technologies we can use. How many of you actually have to deal with big amounts of data in your work? Okay. Well, we have plenty of hands. How many of you actually do work with anomaly detection in some kind of flavors? Okay, we have some hands. Okay, cool. So the plan for today will be to look at some types and flavors of anomaly detection, kind of just understanding what it is, what we're talking about, so that we are on the same line. Then look at the evolution of the technologies, of the tools we have to work with anomalies over the past years. And also look into a couple of specific algorithms, methods which we use today. I will cover ARIMA and LSTM as well as some other things, and then talk what you should use and when. So there is this thing that there is not really a universal definition for anomaly detection. It's kind of like, because it really depends what counts as anomaly or outlier. This definition I took from IBM. So anomaly detection or outlier detection is the identification of observations, events, or data points that deviate from what is usual, standard or expected. So something which is inconsistent with our other data set. But then there is a lot of nuances. However, what we do agree on is we can split those into two buckets. And first bucket is unintentional anomalies. And this is anomalies which come due to errors or noise in the data. So, for example, when sensors which are sending the data, they malfunction due to some issue, there are some data transmission errors, maybe user mistakes when filling in the form, or some environment noise. And usually we try actually to identify and filter out this data which is noise, because it brings some imprecision in our data and later to the analysis of the results which we can do. So it's more or less kind of when your cat movements adds a lot of noise for the cat feeder, whatever you have at home, if you have a cat. In comparison, intentional anomalies is when your cat gets your credit card data and goes and buys extra cat food as well as a coffee. So this is kind of the second type which we have. Those are the anomalies we right now lately paying way more attention, because those anomalies, they are kind of cyber attacks or legitimate business kind of involvement in changes which we want to see, and we want to react to those, maybe fraud or financial manipulations or any other things which go wrong as fast as possible. So we want to raise alarms and want to trigger some automated responses so we don't wait, and it's not just like noise. So those are two different buckets. Technically, the tools which we have can help us with both of them. But of course, intentional anomalies is something which we pay way more attention and put way more effort into. Then, on the other angle, we can actually split the anomalies into three other buckets. And it's also kind of important to understand how to deal with them later. So the first one is a point anomalies. This is a global outliers, when you have individual data items which are outside of the rest of your data set. This can be both intentional or unintentional. But it is, for example, if you're talking about intentional one, when you have a bank account withdrawals which is significantly higher than the previous history and kind of the previous statistics for your payments. It can be, again, you doing some ambitious shopping, or maybe, again, it's someone else using your credit card. Then we have contextual anomalies. This is where the anomaly actually deviates within specific context. So imagine that you have a situation where the home energy usage increased during the day when you are actually not at home. And again, you can blame your cat on watching TV, but maybe there is some other thing which is happening at that point of time, and within that context of the day hours, there shouldn't be increased electricity. And then there is also collective anomalies, where individual, the data is kind of within the range, but when you look at all the data in picture, you have this kind of deviation from the norm. For example, sudden surge in traffic from multiple IP addresses will indicate also a potential problem, which happens like if it's at the same time. So these three, we will come back later which tools you might want to use for each of those. But let's look at the timeline generally, because anomalies have been, we were trying to detect anomalies for quite a long time in the past. And when we go to the early years, let's say before 1970s, where the computing power was quite limited. And data typically came from some kind of factories or quality control situations, or maybe some early scientific research. We were still trying to measure that data and compare it to what is like normal range. And if it was outside of the normal range, we were raising a flag, or people at that point of time were raising a flag. And at this point of time, there were multiple approaches to this. We relied a lot on the statistical hypothesis tests, which kind of relies on math. Then threshold-based rules, we will see a couple of those later. There's also like just mathematical approach. And some control charts where that stuff was visualized on the paper, and then people were drawing lines and trying to understand where like the lines were crossed. So these tools are still used even today, even though they're used often in combination with some more advanced tools, because these tools, like using mathematics, is very, very fast. Then we have the progression with the moment where the computers became somewhat more powerful, to some extent. The anomaly detection became model-based. But these models which evolved, for example, ARIMA, which we are going to talk later, is actually a statistical model. It's still mathematics. However, again, those statistical models, they became more complex and were applied to find weird points in the data. So we got those time series models. It was also residual analysis, change point detection, detect when the behavior changed, which was the point of time when the behavior changed. And then we continued to 2000, where we get way faster computers and also cheaper storage. So now we could access logs, network traces, sensor streams. So we have way more data. We started looking more complex, in a more complex way on all the data. Not just a single weird value, but kind of how it all fits into a context. And here we started getting the KNN methods, so where we actually can compare the distance between the items or the densities of the items, or we can cluster the items and see if the item is outside of the cluster. That might indicate anomaly. Still quite limited, however, it was a progress. And then by now, we have a big data era. So we have a lot of data coming from sensors. We have a lot of also systems which are used for streaming the data, so such as Apache Kafka. And those became normal systems which we use, for example, when we pay with a card at a supermarket, or when someone is using our bank details to make a transaction. So with that, we also started applying the latest deep learning models, forecasting models like LSTM, which we also will have a look at, the transformer models, and other ML stuff which we can use to detect anomalies. So we will focus on the statistical stuff, on ARIMA, and some of the forecasting models from machine learning. But before going into that, what we also will focus on the use case where actually the data is streaming from some point of view. So it's not like we have this bucket of data which is already prepared for us. The challenge is that if we have a new data coming, we can't really compare. We don't know what is in the future, if it's normal comparing to the future. We just know what is right now. So right now, someone makes the payment with your card located maybe in Australia. So, but we don't know if you actually will continue making those payments in the future. Actually, maybe you're already in Australia or maybe not. So, and this is more or less like time series data. So this is where in our data, the one or more variables, they change over the time. And this is kind of creates dependencies between the points, but we only know it till the current moment of time. And the point in that moment probably depends on the value from the past, but again, the future is unknown. And this will impact how exactly we can treat and what kind of algorithms we can use for this particular challenge. So I will also use here a couple of open source technologies. First one will be Apache Kafka. How many of you are familiar with Apache Kafka here? Okay, we have a bunch of hands, probably like 90% of the room. Then we are going to use, to process the data, we are going to use Apache Flink. Anyone knows Apache Flink? Okay, so we have 2.5 hands. Actually, Apache Flink comes from Berlin, from Germany, but right now it's used kind of more globally. So we are going to use those open source technology as well as some libraries. And then we will kind of assume that we get the real-time data, which can be anything from the card payments or stocks, or maybe the driver of the Uber, depending on the route it takes, or something like happens there. So Apache Kafka, or majority of you are familiar. If you're not familiar, it's a platform to move the data across multiple systems. It's designed to be very efficient and moves the data, as much data as possible, as fast as possible. And there we are talking about some tools which produce the data. For example, when you pay with your card in a supermarket again, there is some application which will read the data and then produce the data into a topic. And topic is kind of like a table, not exactly a table. The data is immutable. It's kind of, you can think of it as a post office, so the data is sent into the post office, and then whoever needs the data can come and read the data from that topic. And the topic itself is split into numerous layers so that the data can be read as fast as possible, like using multiple lanes. And what is important for those of you who never worked with Kafka, the data actually is not destroyed when we read it. So unlike queues, the data stays in the topic as long as we need it, either by the time we define that, for example, like for 2 weeks, or by the size of the topic, for example, I don't know, like 10 gigabytes, and then we start destroying older data so that we have the topic maximum size of 10 gigabytes. So this is Apache Kafka. Quite widely used technology. Then Apache Flink is a technology which can be used independently from Apache Kafka. But actually, at least in my experience, we use it quite frequently together because Apache Flink, it kind of sits in the center of real-time data platform. It can take the data which is like real-time data, the movement of the car, for example, on the road. But also it can take the data which is like historical data from the databases. And then it can combine the data and make some kind of decisions or some calculations and then send the data to the next storage, either Apache Kafka topic or a database. So it kind of sits in the middle. It's not exactly, so it's not database, it uses database to store the state if it needs, but on its own, it's more like the engine which computates stuff, but it relies on other storages. So it takes the stuff from the storage, computates the stuff, and then sends it to the next storage. So it sits somewhere in the middle between different points of where you store the data. So this is two technologies which is for our use case, if you want to detect anomalies, it will be very, very handy. And now I wanted to look into different levels, what we can use for detecting anomalies, starting with something which is quite simple, but interestingly, it's kind of actually still used because it's very, very fast. It doesn't really work on its own for anything critical. However, it can be the first level of kind of, okay, something is not exactly aligned according to the patterns which we expect. And the first one is a simple threshold rule which is called 3 sigma. And this is where, for example, someone makes a payment with a card for 300 euros. And we want to kind of have an understanding, is there anything which smells like anomaly here? And the 3 sigma rule assumes a normal distribution of data. It assumes that 99.7% or approximately of data should lie within this plus minus 3 sigma. So anything within this range is kind of potentially, it's kind of the probability of that value is pretty small. So maybe there is an anomaly. And how we can calculate? We kind of use mu plus 3 sigma rule. So we can take the mean daily spend, and I don't know, maybe it's a very, very budget-based person. So a mean daily spend is 100 euros. Standard deviation is 400, for example, in our example. And then when we try to calculate that, we get that the threshold mu plus 3 sigma will be 220. And the new transaction is higher than that value. So flagged as anomaly. On its own, most probably this will not be used because it's kind of first of all, those evil people who try to use your bank details will often split the payments into smaller numbers so that it is not really flagged like that. But in combination with other tools, this works perfectly because it's fast. Mathematics is fast. It's way faster than training a model. Another rule is more or less Z-score. It's equally useful. And it can answer, for example, a question, are 11 transactions within the day is an anomaly? And then we have the formula for the Z-score, where we take the value being evaluated, the mean, the standard deviation, and then we also computate that value. And for example, here, Z-score is 4, based on imaginary values for imaginary person. So we are okay, potentially, 11 transactions is a bit too much for this particular person. So, and again, this is based just on probabilities. So we assume that 99.7% of events should fall within that mathematical probability. And the further it is outside of it, the more problems we expect. But this is not enough, obviously. Then the next level is kind of try to forecast into the future based on the previous history of the event. So we are taking a bit more now, longer history. For example, if this is our expected behavior, then we compare the actual behavior to that, and then we define also the threshold where we kind of think that the actual behavior might deviate from the predicted. And then whatever goes outside of that is potentially an anomaly. And for that, we can use models. Those models are smart, really smart, but they are not really large language models or ML models. Those are statistical models. And we will look at ARIMA model because it's quite interesting because it combines 3 different pieces together. Actually, the silliest thing, it involves so much math. I'm not going to dive deep into that because I did have a number of math classes. I slept through all of them. But we have 3 parts of it. So the first one is autoregressive chunk of this model. And autoregressive chunk, actually, it's attributed to a very smart guy, a British statistician, George Udny Yule, who back in 1927 set a goal to define this mathematical way to model a noisy periodic behavior. And the behavior which at that point of time was puzzling a lot of scientists are the spots on the sun. So those spots on the sun were coming into the view and going away approximately every 11 years. But it was not really like perfect. It was like here and there. And at that point of time, a lot of mathematicians, they really were defining periodic behavior is more or less the behavior which is kind of strictly follows some periods. George Yule, he is like, okay, actually noise is not a problem. So he analyzed real data with cycles and noise and developed a model. So he created a mathematical way to model this noise periodic data, and his work is actually attributed to this autoregressive model, which kind of help us through mathematics to show that we can use the past values to predict the future. So we can kind of use the data to predict the future to some extent. On its own, it was used. However, it's more powerful if we add into the mix moving average. And I don't know who actually came up with all those names for those models, because somehow they're a bit misleading. But anyway, moving average is attributed to Evgen Slutsky, another mathematical statistician, who more or less in the same year, he actually showed that some random shocks in data, something which is unexpected, for example, sudden changes in consumer behavior, or some weather, or wars, at that point of time and also nowadays, if we smooth them over time using a moving average, we can get a wave which actually looks like a cycle, and it's not really, so it looks like a pattern. So even though the original data looked very, very random. So in this way, he showed that errors themselves can have patterns. So, and with using his model, we can use past mistakes to improve future guesses. And those 2 models can be combined. And it was tried to be combined by these 2 guys. However, there was a problem that the data which is analyzed by those models should be stationary. And this is kind of a bit complex to understand, or at least like I looked into a lot of how exactly we visualize the stationary data and what is comparison to non-stationary data. And generally, on the day-to-day, we use non-stationary data. Our data has trends. So the best way probably to understand the stationary data is to think about your bank balance. You usually have trends upwards, or some of us have trends upwards, because we add salary each month. But if you model the raw balance, it's not stationary. But if you look at the monthly change in balance, so some kind of a change which you had extra money each month, or you have less money depending on your financial situation, then the data is more stable. So the idea is to have this difference in the data. We don't take value as it is, we try to compare it to the previous value. And in the end, we have the mean more stable. And we just, for example, the stock price, we compare the stock price of the next day minus the stock price from yesterday, and we just have that difference in between those. And sometimes we have to apply the difference in a couple of times to flatten the data. So we remove all the trends, we remove some important details. However, it really helps us use this ARIMA model. When we are using the ARIMA model on our own, we don't really have to overthink it so much, because a lot of libraries actually do that part of job for each of the chunks for us, even though each of the chunks involves some extra variables which we can adjust to kind of, if we know our data, so we can kind of tweak it a bit. There are a number of libraries, and here I looked only at Python. I must admit I'm a JavaScript developer. Whenever I can use JavaScript for ML, but the things actually are way more advanced in Python, even though JavaScript is catching up. How many of you actually are, let's say, JavaScript developers? Okay, so we are in minority. How many of you develop in Python? Oh, okay. How many of you, we have still not raised hands, C#? Oh, I see. Okay, so Python. In Python, we have 3 libraries. We have PMD ARIMA, which actually I use because it's super, super simple. But we also have stats models, which is kind of very comprehensive, super smart library. It has a very big statistical toolbox which we can use. And also we have skTime, which is kind of a modern one, really good for experimentation, kind of at scale and comparison between approaches. So we have a number of libraries which you can use. And the ARIMA itself, yeah, I think it's kind of a, because to train your model, you need to have less data than training machine learning model. So in a way, it's pretty straightforward. So if we have, for example, the data coming from Kafka here, and I'm using Flink as an environment where we are making those computations. So this is kind of our, I don't know, like, not exactly hardware, but some kind of a basis where we are going to run the library. We will take the data window. The data window, we will run anomaly detection method, which we will define in a second. We can retrain the model periodically on the historical data which we have, or we are taking the values which we already kind of calculated before, use that to predict next values, compare the prediction to the actual values. So kind of we try to forecast into the future. And then when we forecast it, it's like, okay, does it really like, what is the difference between the forecasted and reality? And then we bring the data back. In this case, I think the data back to Apache Kafka, the results. And for example, if I would took some kind of stock value, this is a bit of Python code for Apache Kafka, creating environment, getting the source, and then processing the data. And the source is taken from Apache Kafka, from a specific topic with the stock data which I had, and then sending the data back to Apache Kafka. And the anomaly detection method itself, we are figuring out if we have enough historical data, because we need some data to train the model. So it's still less than what we use for machine learning. However, we really need enough data for the predictions in the future. We train the model if we want to train the model, so we do it periodically so that we have kind of a fresher value. If not, we just forecast and then compare. So this is ARIMA model. We use it in the company as a fast way to determine anomalies, and also where you actually really don't have to train something more complex as machine learning model. And it works actually quite well for a number of use cases which may be not as critical. If you have something critical with something more nuanced behavior, you can use machine learning model. And here we are going to look at the LSTM model, which belongs to deep learning models. And LSTM stands for a long short-term memory. So it's make sure that we remember important stuff and forget not important stuff. And it kind of falls into this prediction problem. So for example, given a lecture, we need to predict the next one. And it's kind of like at start, it's a bit like tricky, but the more information we have, the easier it is to say what will be the second part of the sentence. So that's why we train the model on, so we train the model generally on some bunch of data, and then we give the model chunks of information, and it tries to predict the next character or the next value, whatever we have. So LSTM, anyone used LSTM in the past? Oh, we have. Cool. So LSTM is part of recurrent neural networks. And in basic recurrent neural network, each step in a sequence, for example, like a word here, produces an output and also a hidden state. So, and that helps us then to pass the hidden state to the next step, helping the network to remember previous information. But RNNs, they are super, super smart. However, there is a problem. Basic RNNs forget too quickly. So they struggle with long-term dependencies, like remembering the start of a very long sentence. By the end, we come to the sentence. So LSTM introduced a cell state to fix that. So now the network can decide to update or erase part of the state cell. And for this, we introduce several gates. So we have an input gate. It's like, do we want to add extra information to our memory? Is this important? Then we have forget gate. Should we forget something because it's no longer relevant? And output gate, which part of the memory should be used to generate the output. So a gate is kind of a smart filter. And the gates itself, they are learned during the training so that when later the model reads a sentence, the cat, which was very smart, sat on the table or whatever, it knows that the word sat is important, but the word cat, which is quite similar, is also important. So it shouldn't forget cat, though there is a number of words in between those. So LSTM helps with that. It also helps to eliminate all kind of filler words or whatever we don't need, if we are talking about text. And just like other neural networks, LSTM has weights and biases, and it has more than a usual neural network because it has this extra gates. And we train those how to open or close the gates by analyzing a lot of data. So the more data is analyzed, the better like we know which gates were to open and close, or which information to forget, which information to remember. Yeah, so LSTMs are widely used in text like sentence prediction, language translation, and also in numeric operations. So here, for example, we can take, again, the data and read the data from our real-time stream, process data by Windows, and then run anomaly detection, create the sequence, reconstruct the sequence using LSTM model. Again, we try to forecast into the future. And here's the LSTM model. You need to pre-train that model. This is actually the training itself comes with a bit more cost, but you need to pre-train that model, maybe retrain from time to time. We can use some kind of storage for this. So, for example, I was using the data stored in Iceberg so that I could get information from Apache Kafka. And with that, we can then reconstruct the sequences based on the data stored based on the data which we have in the model, and then we can report anomalies. So there are a number of libraries. I was using TensorFlow, and actually that's also my appreciation of using TensorFlow also in JavaScript. So here I was using TensorFlow, but there is also libraries which allow to have LSTM usage like PyTorch and others, again in Python. Yeah, I have a bit of kind of, even though I use, for example, in JavaScript a lot of stuff, I still feel that TensorFlow in Python is way smoother than when I'm using it with JavaScript. Maybe, again, I will change my opinion. But depending on your language, right now we have more and more tools which work with ML models, but again, some languages are easier than others. And then in the code itself, we define the model, we set some properties for that model, we train the model, save the model. This is better to do outside and in advance so that you have the model trained. And then when you are actually getting the data, you use that model to predict, to forecast the value, and then to determine if it is according to what you expected or not. So those three options which we had, like mathematics, then ARIMA, and then LSTM, like those are within different, would say, like timeline scale, historically evolving. But those all, they actually are used in practice quite frequently. And the challenge is that anomaly detection is not really like, if you have your own like use case for anomaly detection, it's probably quite different than use cases which other people have. Because your anomalies are different, maybe severity of anomalies is different, maybe also like how fast you need to respond to those anomalies, how frequently data changes. So, for example, if you have this point anomaly, if you suspect isolated outliers, maybe the simple statistical threshold or unsupervised outlier models, they will be more efficient and will give you very, very fast feedback. But then if your data has kind of a seasonality or known contextual patterns, so you kind of know how the electricity usage changes over time or something like this, then you can use the forecasting models, and especially those which are ARIMA. So with ML, we also use forecasting models, but statistical models based on the math will be still faster, significantly faster, and training of those models will be cheaper. And then if you, of course, have kind of some complex patterns and very sensitive information, I don't know, like fraud detection, where you have to be quite, or like the model has to be quite smart to trigger that alarm and not to miss information, then maybe you should go for the machine learning. But the thing actually is that often we actually use those methods together. So at least this is what I see at Confluent. And all the patterns. So we use those methods with data streaming. The goal is to get the data as fast as possible, to process it as fast as possible. But in the end, you actually combine to have kind of maybe the first layer to use some mathematics just to kind of shuffle and see what is kind of has potential to go wrong. Then for forecasting, for maybe like logs or some network issues, you might want to use ARIMA. And then for some more complex situations, I see that our data streaming platform is used in combination with AI and ML. And actually, when we use ARIMA, also behind the scenes, we use extra ML features on top of it. So that's the story from me. I have some links in the papers and some other materials which I used, as well as for those of you who are Kafka people, Flink and Iceberg, you can also see how well you know those technologies by running this certification. It's a free certification. It's just more or less fun to evaluate your knowledge of the technology and then get certified if you want to. That's it from me. Thank you so much for being here. And we have time for questions if you have any. Or if you don't, I will be still around. So feel free to grab coffee. Are croissants still there? Anyway, and ask all the questions about anomaly.